accomplish this course, you will be able to describe the background of SR, the technology advantage of SR, basic concept involved in this SR, and you will be able to describe the wording fundamental of SR. And also, you will be able to understand the basic configuration for SR-MPRS. But this SR-MPRS is without the controller, just the static SR-MPRS configuration. But anyway, so this slide will be 5 sections. Segment routing overview, fundamental, kernel protection, and typical usage, and some configuration. Let's look at the overview first. So why we need SR MPRS? Why we need it? It is all the reason is hide in the shortage of the traditional MPRS technology, the LDP and the RSVP. LDP, actually, we already mentioned before that the LDP had a problem. First, the LDP itself does not have the path computation capability. This is what we just said. So it only following the IGP shortest path to do the forwarding. For the most of the network, it will be okay. But as we said before, now more and more services is put into the cloud, which means in the one network, in the barrier one network, the traffic is increasing. That means we maybe we were facing the possibility that barrier one network will congested. So without the capability to control the path, you will got problem. Okay. Secondly, both IGP and LDP need to be deployed for the control plane, which means if there's something happened, like when for example, wait, let me open some. Let me open the Paint. It means that okay, in this topology, it means, for example, I have wait. Let me select the. It means the LDP and the IGP, they are both standalone protocol. And if this situation happened, you're going to say there's a problem. For example, the above link is the main link. This is main. This is a primary link. And the below one is a backup. Okay. Now, if the primary link is failed, the path will switch over to the backup link. So the LDP thinking, okay, I should go below. Because IGP think I should go below, so the LDP actually also was thinking go below, because the LDP by default, the LDP using the what is that, the liberal way to save the to save the labor path, to save the RSP, which means LDP by default it got the backup path. So if the primary path is failed, the LDP can very smoothly, very fastly to switch to the backup path. There will be no problem. But if the primary path, this is recovered, it will got a problem, because the IGP above the IGP will convergence speed is more faster than LDP. The IGP is finished the convergence. The IGP is finished the convergence, but the LDP depends on the IGP's result to calculate the RSP. So which means the IGP is finished. While the IGP is finished the convergence, the LDP is still not. The LDP thinking the path is still below. So during this time, if there's a VPN traffic, MPRS VPN traffic is coming, so based on the router, based on the root entrant, the IGP said it should go this way. But if I want to go this way, the LDP here might not be finished the convergence because the LDP convergence time is absolutely slower than the IGP because LDP based on the IGP. So during that time, the MPLS VPN traffic cannot forward out because there's no LDP. There's no LDP session here from go to here. There's no LDP session from this way. So you will create a certain point of not certain point. You will create the packet rules. There will be some packet will be discussed during that time. So this is the problem. This is the two problems that LDP facing. Although we can have some way like we can do the LDP IGP synchronization, we can do that, but it's just difficult to do the maintenance because I need to know like every router need to configure it. Not a lot of devices will do that. So this is a problem for LDP. And so for MPLS, there's another protocol. The ISVPT also can create their LSP, but ISVPT also have two problems. Yes, two problems. First, ISVPT, it is a protocol. Since it is a protocol, we need to have some package to keep alive for the ISVPT neighbor. And also need to have some packet to always reserve the path we just applied before, or reserve the resources we applied before. So those signalizing need to continuously send, so it will waste the time, waste a certain bandwidth. Secondly, as we said before, the ISVPT, this kind of protocol, it is ask the devices to do the calculation, do the path calculation by the device itself. It is distributed calculation, which means the path you calculated might not be the best path. For R1's understanding, this path might be the best, but if you look at the whole picture, it might not be the best one. So this is the problem that the problem that MPLS, LDP, and ISVPT have. So there's a solution, of course. The solution will be the SR. The solution will be SR. And that is just the first reason why the SR is being needed. And secondly, there will be another reason, service-driven network. Because as we said many times, the network nowadays is not just for connectivity. It's just the connection. I created the connection is not enough for the network. This network nowadays need to guarantee the SLA. So how to make the for example, there's different traffic. and different traffic might have different requirements. And I want to create a tunnel from one point to another point, one P to another P. How can I make sure that this tunnel is enough for certain services? And if this path got a problem, how can I make sure? How can I dynamically change the path? So this is second reason why we need a segment routing. Okay, so let's look at the what is how do I say this? How is SR solve the problem that we just mentioned before? First, the SR will simplify the protocol and extend the existing protocol. The SR extends the IGP protocol, and it will ask the IGP, which is ISS and OSPF, of course. BGP also can, but BGP will use the between the AS. Inside the AS, we will use OSPF and IS and ISS, not IS, is to carry the label, distribute the label. So we do not need to use the LDP. We will ask the IGP to carry the label information. So I just simply create the IGP label relationship between them, and I will ask IGP to carry the label. BGP is used between the AS. Okay, For example, this is AS1, this is AS2. I will ask the BGP to help us to carry the label. And this is just for LDP. And second, for the SVPT problem, SVPT, how to solve the SVPT's problem? So first, for the segment routing, it is a source routing mechanism is involved for the segment routing. So which means I can tell the source node how to forward the packet from R1 to R3. That's all. And for R2, R4, R3, they actually do not need to do the calculation or do not need to know from R1 to R3 what is the path. And this forwarding path will be calculated at the controller, and the controller will send into the router. Will send into the router, and the router will know. So it will be no problem for the SVPT. There's no any signal line need to be sending, need to be forwarding, need to be exchanged. And also I can planning the path based on the controller. And about the second problem, this one, the service-driven network. Since we're using the controller, and then in the controller we can define, like for this path, what is the time delay, what is the bandwidth it need. Okay, in some case, maybe there's a traffic coming and make this link is, for example, congested and cannot fulfill the requirement for services. So the controller will get those information and automatically ask the R1 to change the path. So there will be no problem. So this is all thanks to the working principle, the idea of SR. Those kind of way can be achieved. Okay, so you can say the SR solution. So basically, as what we said. And also there's some protocols involved. There will be BGP. BGP will use to tell the controller to upload the to upload the protocol to upload the topology, the bandwidth usage, etc. Those kind of information. And we can use PCEP and the netconf to deploy some configuration for that. That is the whole picture. But without the controller, the SR solution also can work. No problem. Okay. So a little bit of overview for the SR. SR designed to forward data packet on the network using the source routing module. So it's very important. And SR divided a network path into several segments and assigned a segment ID. So how many segments they have, we will talk a little bit later. And the forwarding path will be just segment by segment. Okay. And SR encapsulates segment list in 4 that identify a forwarding path into a packet header. So at the beginning of the devices, at the source node, they already know the whole forwarding path. And they also can do ECMP, by the way. So SR has following characteristics: extending existing protocol to facilitate networking evolution, support both control-based centralized control and forwarding-based distributed control, providing a balance between the 2 control modes, and enable network quickly interact with upper-layer applications through the source routing technology. Okay, some advanced. First, simplify the control plane. This is of course. Secondly, we can use the FRR or HSB or some other technology to enhance to protect the SR kernel. And of course, we can use SR to replace the MPSD, of course, enhance the network capacity, expansionable capability, and a smooth evolution to SDN network, because if you use SDN network with SR, you will you will find the SR will be very easy to use, very easy to control. Okay, so this is overview. Let's look at the routing fundamental for the segment routing. Also, okay, so first, what is segment? Segment basically just a path from one point to another point. There will be a path. So this is a segment. Segment. So segment, let's say, represent an instruction to be executed by a node for receive data packet, and the instruction is encapsulated in the packet header. So segment, so for example, I got instruct 1, 2, 3. So each instructor is tell us this packet should sending to where. So this is segment. For example, R1 is sending to R. The instruct 1 is from R1 to sending to R4. So you might have two paths, path 1, path 2. If they are ECMP, you can do the ECMP. And the secondly is from G02 from R4, this interface out. So I will send out. And for the instructor 3, it is sending to R8 with the shortest path. So R6 will send to R8. So based on this instruction, based on this segment, actually, we can see we can forwarding from one place to another place to another place to another place. Then the packet will forwarding to its destination, right? So you can see the idea is not difficult for the segment. So how to describe the forwarding path? How to describe the segment? We can use something called segment ID. So this ID is it's just like label for the SR. For the SR, it's just like label, like 1,000, 10,000, 10,001, 10,002. This is just a number. It's just a label. So for example, I still want doing the same thing, and from sending to R4, then sending to R6, and sending to R8. And first from R1, I want sending to R4. I no matter use which path, it's going to R4. So I just give an instruction 400, and R1 will send into 400. Then the second instruction is I want to send out from G04. Then I will put another label 1046. If R4 receives a label called I1046, the R4 know I should send out from G002 and sending to R6. In R6, it looks like okay, the destination is 800. That's segment ID. So it will send out based on R6 LSP table. We just forward. Okay, it's just that. This is segment ID. And those segment ID will be added at the beginning, at the south of the node. We call this is a segment list. Yeah, here is segment list for this. Segment list. So you can say 8, 1, 0, 4, 6, 400. So you're gonna say this packet is just like sending this from to here. So this 400, the R4 node it is sending to myself, and it will read the second. It will remove the outer MPS label and read this inner the second label, and it says I want to go 1046, and R4 know 1046 means this interface, and they send to R6, and R6 read that the destination seed is 800, so it will send into 800. South routing, right? South routing at the very beginning, at the south, I already know how to send it, how to do the routing. Okay. Okay. So the segment actually have different type. The segments have different type. Okay. So the first type is called prefix segment. Prefix segment basically means a root entry, a bunch of network. That is prefix segment. For example, this 10.1.1.0, it means this segment, I give it a number 100 16001. Okay, and those loopback will be used as a node segment. Node segment means the device itself. It means device. It means the device. Normally is mask length is 32-bit long. So this segment is a special prefix segment. We call it the node segment. We call it the node segment. Node segment means the device itself. Okay, the device. So there's another segment called adjacency segment. Adjacency segment means interface. This interface or this interface. So for the prefix segment, it should be, not should be, it must be unique for the whole network. It must be unique. Like 100, 200, 300, 400, it cannot be same for the whole network. But the adjacency segment, since it is only means the interface for device itself, it's a local idea. So the adjacency segment should be unique for local devices, but in the whole network, this can be same, no problem. No problem. Okay. Okay, so here's some example. This is prefixed. Here is a node segment, prefix segment. But node segment is just a special prefix segment because node segment is just means 32-bit long root entry, and this is like normal root entry. Okay, and there's another concept called sRGB. sRGB stands for segment routing global block. So what is that? It means this is sRGB means the SRMPRS label zone. For example, I have sRGB from 15000 to 20,000. So from here to here, this is where segment routing can use. So which means when we do the configuration, we needed to define like how many, what is the area, what is the area, what is the label that segment SR MPRs can use. So like why we need to design the, why we need the sRGB? It because maybe at a different router, the MPS is different. The MPS left, the label left is different. For example, in R1, I only have I am using from 1 to 16,000. This is R1 already used for MPS, LDP, SVBT. So what so the left is from 16001 to, for example, 1 to 20,000. Maybe this is in R1. This is the segment left, but in R2 might be different. So we needed to define different sRGB. To define different sRGB. And here brings us another problem, is that maybe our sRGB is different, our label area is different. So what if that for the R3, the node segment on the R3, it is thinking it is 20,001, but at R2 and R1 for sRGB, there's no places for this label. The range is in R1 is here. The range for the sRGB in R2 is like this. But R3, the sRGB range is like this. There's no, how do I say this? There's no coverage for each other. It's not overlapped. I mean, so what if R3 the number is 20,001? So in sRGB, there's a the seed, the segment ID. This segment ID is working like this way. I configure a segment ID. I actually do not configure a label. I actually do not configure a label. Oh, sorry. What we do the configuration, it is a label, but this label will become an index. For example, in R3, we know our sRGB is 20,000 to 21,000. And in R3, I will configure, for example, this segment ID will be 20,001. So the R3 know this index is 1 because it came from here to here. The index is 1. So the R3 will tell R2 that going to me, the index is 1. So the R2 will thinking the R3 node segment is 12,001. And R1 thinking going to R3, the label will be 16,001. You guys got the idea, right? I only send out the index. It is because that at every devices, the sRGB they can use is different, might be. So when you do the planning, like to see, okay, if the node ID is the node segment, whether they are duplicate or not, you should depends on the index. Okay. Okay. Let's continue. And there's a adjacency segment. As we said, adjacent segment means the interface, like which interface I should send this packet out. Should I send it from 101 or 102? Okay. For those two concepts, any questions? Those two concepts is very important. Okay. 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 So let's continue. Wait a moment. Okay, there will be some other like intra-AS propagation for the node city and adjacent city. One word, they are using RSS and OSPF, extended RSS and OSPF to carry those kind of information like the adjacent city and node prefix city and adjacent city. Okay, they just use RSS. Extended IGP. They will have some new TLV or new type of OSPF router to help us to do it. But you just know this will be enough. Okay, here's some OSPF TLV, ISS TLV. I will not jump into a detail. If you are interested, you can check this table. Okay, just some. This is some example. Okay, then there will be another important concept is called SRMPS. Sorry, SR policy. SRMPS policy or SR policy. SR policy, basically, SR policy just a new way to establish a tunnel, to establish, to forwarding, to how do I say this, to tell it's a new way to tell the source node how to do the forwarding. That's all. That's SRMPS. Okay, it's not something special, just a new way to do that. For example, so you can say in the source point, there we need to tell the R1 like how to do the forward. For example, R1 wants going to this network 1220, this network. How is this segment list being created? We can use SR policy to tell the R1. SR policy basically is some way to do it. Okay. There's some routing protocol to deploy this. But anyway, about SR policy, here we will talk. Don't worry. But anyway, no matter you use the SI-MPS-TE or SI-MPS policy, anyway, for the source devices, you got this list, and based on this list, we can do forwarding. For example, R1, it receives the packet, the first label is 100. Okay, the R1 knows it itself and pops this first label, and based on the second label, 1012, it knows, okay, I should send out from this interface. So I send out, and also remove this label and send out. And R2 receives the label 1002. R2 knows that, okay, 1002 means this interface. I send out from this interface. And also I will remove this. And it will receive 1002. And R3, when it receives 1002, R3 know that there's a network. Segment ID is this. So I send out from this interface. Then it reaches to the destination. This is how the SI-MPS, TE, and policy, both of them, how did they do the forwarding like this? Okay. Okay, and about the SIV6, tomorrow we will talk about, we will introduce the detail about SIV6. But here you just only need to remember one conception is that the SIV6 simplifies the boarding plane. About the SIV6 later we'll talk. Tomorrow we'll talk. Here's some how is this behavior of the SR. It's not behavior. I mean a special behavior. Besides the pop, besides the push pop, here's another behavior for the label stack. It is called stitching label. What is stitching label? So you can see, since the SR, actually, we have this label stack, right? We have a label stack. And each label, the length is how many? 4 bytes, right? 4 bytes long. So if we create, if we stack a lot of label at the R1, which means the header will use a lot of bytes, which normally it will be used by the real data, but now it is being used by the header. So which means the efficiency to do the forwarding will be dropped. This is one reason. And secondly, for the device, how many label it can read, it can detect, it can read have limitation. This is based on the devices. The devices have some limitation at how many label it can read once. So which means that you cannot put too much label in the label stack. It will cause problem. But what if we are facing a quite large network that we need, for example, we need 20 hops to reach to the destination? What to do about that? So we have some called stitching label. We'll put a stitching label here. So when the R1 sending to the R2, the R2 will know, okay, this stitching label means this label. So I will add this label into the header of the devices and continue forwarding. This is called stitching label. This will be normally used between the AS or between the area. Between the AS or between the area, we'll use this stitching label function. Like if you thinking that maybe the depth of the label stack is too deep. Okay, here's a basic concept, and let's look at fundamental. First is how are SID used. First, combining prefix, node prefix, and adjacent SID in the sequence can construct any network path. We already checked it before. Already gave the example before. Yes, look at this, right? Every hop on a path identifies the next hop based on the top seed in the label. Of course, this part we already talked. Seed information is stacked in sequence at the top of the data header, and if top seed identifies another node, the receiver node forwarding the data packet to that node in ECMP mode. It's very important. So the SR can do the ECMP. If the top seed identifies the local node, the receiving node removes the top seed and processes with the follow-up procedure. In real world, prefix segment and adjacency segment can be used separately altogether. Okay, so there's some scenario. First, it is a prefixed scenario-based forwarding path. So, which means I only define the prefix seed. So the R1 only based on the prefix seed, they only have one out label, then do the forwarding, out to R2, then R2 will receive it. Okay, so this actually is what we call the SRBE, this one. This one is here. This is how SRBE do the forwarding. Second is adjacency segment-based forwarding, which means I only, based on each device's interface, I was doing the forwarding. For example, 1023, this is 1023 of send out, and the secondary is 1034 is here, send down, and then 1056 sending out from this interface, and then here. This is if you are familiar with ISBPT, this is what we call the strict explicit path, right? Each hop I define, I limited the forwarding path. I define the forwarding path strictly. The second is we also can use this adjacency plus node segment based forwarding. So some path is based on the node segment. I send to here first, then based on the adjacency, then based on the node, based on your requirement. Okay. So as we said, the SRMPSB actually is the first scenario. We just based on prefix segment to do the forwarding. That is what we call the SRBE. SRBE is I don't care like which path you are forward, as long as this packet can reach to the destination devices, destination network, it will be okay. This is SRMPSBE, okay? And another is called SRMPRTE, or you can call it SRMPS policy. Anyway, SRMPS policy is just a new way to create a T tunnel. Okay, so SRMPS TE, they have the label stack. They have the description of the path. This describe a path, right? So they have SRMPS TE. They have the capability to control path. So two things: BE and TE. BE do not control path, only from one point to another point. TE control the path. So SRMPS BE, this actually is an advantage version of the MPS LDP. It solves the problem for MPS LDP. And SRMPS TE is replace the MPS TE, solve the problem for MPS TE. Okay. Okay, so let's look at the forwarding. We call it the working principle. How is doing the forwarding for SRMPS? Okay, so MPS first, for SRMPS BE, first they needed to advise the seed, the prefix seed. When I got the prefix here and the prefix index is 100, so it will forward, it will, as we said, it will only advise the index 100, index 100, index 100. So in R1, it knows that if I want to go into this IP network, I should sending to 30,100. because in R2 it knows the 100 here. So R2 also same, incoming 13,100, outgoing 40,100, because this sRGB is from 40,000. So sending to R3, R3 will know, okay, this in, this out is sending to R4. And R4 knows that, okay, this 100, index 100 means this root entry, I should forward out from this interface. So this is about the SRMPSB, LSP, how does it create the LSP, and basically how did they do the forwarding? Pass. You can say the forwarding procedure is like this: push, swap, swap, pop. This just looks very similar to the MPLS LDP, but you can say all the devices know the label, know this index. Okay, I guess it's not difficult. Okay, so let's look at the TE. So TE, as we already talked about what is TE, okay? So basically you just control the path, but TE also can provide some kind of protection function, right? But enough about, here's a little introduction about the TE. So, so basically TE working like this way. Use RSS and OSPF to how do I say this? To advise the network situation, like the topology, the bandwidth it used, like the cost for the IGP, etc. Those kind of information. We will use extended RSS and OSPF to extend, and based on the requirement, and based on those information, they create a TE database, and based on the requirement, device itself will do the calculation, and after the calculation, they will using the ISBP to reserve the resources on that path, on the calculation, on the pathway calculation. We will use ISBP to reserve the resources. Then the packet can do the forwarding. This is a T. What did T do? What did T do? And SR, they put the calculation part. They put the calculation part in the controller. And about collecting the topology, the bandwidth, usage, etc., those kind of information, they're still based on the network device. Still using SS and OSPF. They'll put into the local TE database. And this TE database, what is it used for? It will use BGP-LS, this protocol, to send into the controller. Controller doing the calculation and tell the devices what to do. What is your segment list should look like if you want to go into a certain network point. Okay, then you can do the forwarding. So you can say SR MPLS-T compared to the MPLS-T, the controller, I mean the path calculation, this controller, where it belongs at controller. So device itself do not need to do the calculation. So it simplifies the controller. That is the reason. That is why we call it to simplify the control plane. Okay, a little bit of comparison, but this part I pass. If you're interested, you can just check this table. Like what is the pros and cons for SRMPST and SRVPT. But in this slide, I just want to mention one thing. I just want to mention one thing. RSVPT, for example, you want to reserve a path with 10 megabits bandwidth. The RSVPT can help the devices to reserve 10 megabits. That this 10 megabits just dedicated to certain traffic. The RSVPT can do it, but SRMPST cannot. The SRMPST basically only can calculate the path, but these devices, when it send out, I can, for example, I only want them to use 10 megabit, but there's a 100 megabit traffic came in. The SIMPS cannot control. It will forward 100 megabits out, but for the RSVPT, it can control. That is different. That's one big difference. That this actually is an advantage for RSVPT. The shortage for SIMPST. Other feature, the SRMPST is much better than RSVPT. Okay, except this bandwidth control, this one, even you use controller, we need some other technology to guarantee that the traffic will not take too much bandwidth. RSVPT can, but SRMPST cannot. Okay. Okay, let me continue. So SRMPST, how did they collect the information? Two ways. One is controller is in the same network with in the same IGP, in the same as with the device. Then we can directly use extended IGP to sending the topology information to the controller. But this is not recommended because in the real network, you may be facing inter-AS network. There's an inter-AS. There's another AS. Should I still configure the IGP? No, we will not use it this way. So this very used, seldomly used. Most of the time we will use this. We're using the BGP-RS protocol to upload, to sending the topology information. Okay. Sending up here to the controller. I use the BGP-RS. The BGP-RS will collect the information for IGP because every devices they have the same RSDB, right? Because we are the ISS or OSPF devices. We have the same RSDB. So I just put this RSDB into the BGP-RS. This what do you call this this address family, and use the BGP to tell the controller. That will be much more better. So this is where we use in the real live network. Okay. As for example, R4 this interface is here. R5 this interface is this. So I will tell the controller. I'll tell the controller. So that's all. So this creation, how to create SRMPST RSP, how to create this RSP. First, of course, you can do the calculation based on the controller, or you do it by yourself, which you create the static RSP. Okay. And but if the traffic won't go into the T tunnel, for SIMPST, if you configure SIMPST this way, you need to create a tunnel interface first. It's like this. You need to create a tunnel interface. This is a manual way. This is a netconf, which means controller way. But they're similar. No big difference. They're similar. Okay. We need to control a tunnel, and inside the tunnel, set the IP address, set a protocol, set a destination, tunnel ID, signal protocol, etc. So you can say SRMPST this way to create the SRMPS path. There's a lot of configuration you need to deploy. This looks like just a little bit, but think about that in live network, there may be a lot of kernel is created and deleted, and you need to use the netconf to deploy those configurations. Very complicated and costs a lot of time. So what to do? There's a new way. This we just passed. Kernel. Date forwarding we already said. This is for disadvantage. There's a disadvantage for the SRMP ST. So there will be another type of way to achieve SR is your SR policy. Use SR policy. So SR policy, the good side compared to the SR-MPST, compared to this, SR-MPS policy do not need to create a terminal. Do not need to create a terminal interface. There's no need. So what to do? The SR-MPS have a tuple called the header, color, and endpoint. Header is the source node where this traffic came to use the SR policy kernel. This is head end. And then another devices will be endpoint that which is a destination will be endpoint will be another PE, PE1, PE2. This will be the end. So head and end, then with the color, we maybe have a lot of terminal forwarding between them. Each of them have a different color. This color basically just a number. For example, 10, 12, 14. Three number. This number means color. That's all. So when I do the forwarding, for example, I want to go into this certain network, network 1. I just need to ask the network 1 to carry the color 10, tell the header. And header will know if I want to go into the network 1. It look into the color of this network 1. It looks like, okay, it's 10, so I should go into the 10, number 10, this color 10 terminal. So you can see it is very similar to the terminal ID. Think about the MPLS terminal ID. You'll find the concept is similar. Okay, so policy, they will use extended this what do I say, this BGP address family for SR-MPLS policy. So for SR policy, you only need to create the SR policy neighbor relationship with the ingress, with the head end. It will be enough. Because you only need to ask the head end to have the segment list, it will be enough. In the middle devices, they do not need to know the segment list, right? So I can directly do the forwarding, no problem. Okay. A little bit architecture. So it's like this. We will use a BGP-RS to tell the controller like what is working topology and all other information. And then we'll use a BGP SR policy to deploy the SR segment stack into the egress. It'll be okay. And then netconf will have some other configuration, like what is the VPN RD, VPN RT, those kind of information. We will use the netconf to forward to the ingress. Okay, so it's like this. It's a solution architecture like it. And for the SR-MPLS policy, we have the module like this. First, we have a primary path and a backup path, which means for the SR policy, we can use two paths. One is active, another will be standby. If this one is filled, I will directly switch to backup. And for each, we call this as a CP, candidate path. Okay, candidate path. And inside candidate path, we can have multiple segment list. Okay, we can have multiple segment list. So if we choose the primary path, we can choose like one segment list. We can choose all the segment list based on the weight. If the weight is same, we will do the load balancing. Okay, so let's continue. And for the SR policy, we can use sometimes we need to configure what you call it, we can do the static configuration. We can do the static configuration. So this binding seed means the node seed, like node seed. What is a node seed? What is a node seed for you? But you also can configure the adjacency seed, but here we do not have the example. But tomorrow when we talk about when we do the demonstration for the SRMPS, you will see like if you wanted to configure the adjacency seed, how to do the configuration. No big problem. Okay, so continue. So here, let's look at the SRMPS policy service process. First is for information collection. The information collection very simple. That at the very beginning, we will use like the OSPF and RSS to exchange the topology information like with each other. And then they will tell the BGP. Sorry, no, not tell the BGP. I mean, the BGP will get those information and tell the controller. Then controller know everything. Now they wanted to create a path from here to here and to here. And here have some network. Some network. For example, 5555 is this. So I need to ask R1 to go into this green tunnel. So the controller will use a netconf to tell the R3, because R3 is a PE, to tell R3 that for this IP segment 5555, if you want to send out to another PE, give this router a color green. So this will send out to R1, and R1 will know I want to go into 5555. I should go into the tunnel. This packet should be carried by the tunnel with color green, which means this tunnel. Next hop is this. So R1 will later when sending the packet, sending to R1, R1 checking, or if you want to go into 5555, you should choose the green color tunnel. Go here, go into R3, then send out. Like this. This one we already taught, root advised. And the controller will give R1 this green color tunnel is what is the forwarding path for this green color tunnel. Then R1 will do forwarding. Traffic was forwarding. Okay, so that's all. This is for the SRMPS policy. The most important idea would be that like this. This is a little bit summary. We just pass this. So any question for the fundamental about the SR? Any question? Okay, no question. Uh, okay, so if no question for the SR, then let's take a short break. Let's take a 10 minutes break. Then we will continue to talk about the SR root internal protection and detection technology. Okay, let's take a short break. Okay, so let's continue to talk about the kernel protection and the detection technology for the SR kernel. Okay, so for SR kernel, we have two type of protection here. First is local protection. Another is end-to-end protection. Local protection, as we said before, as we mentioned before, it means if link or node is failed, I can bypass this link or node to forwarding traffic. This is local protection. Local protection, most of the time we use is TIFA FR. Any custom, not a lot. Most of the time it's just this. Here, this is a technology, but not used too much. End-to-end, mostly just hot standby. Just hot standby. Okay. Okay, so first TIRFA. TIRFA FRR. What is that? Before we answer this question, why we need a TIFA, we need to have an idea about what is the problem with FRR. Why we need FRR? What is the problem with FRR? Let me draw another picture. Okay, let me create some approach. Let me think. Here, 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 and here. Okay, this is R1, R2, R3, R4. And behind R3, there's a network 1. And the cost will be 10, 10, 10, 100. Okay. First, for FR, to understand why we need a TIFR, we need to understand what is a macro loop. Macro loop means this. For example, R1, by default, its best path will be this, will be forwarding like this. And the backup path will forwarding like this. The R1 thinking like this. Okay, now in the future, the link between R1 and R2 is failed, so the R1 will immediately switch into the backup path from R1 to R4 to R3, then it's sending to R4. Now here will come a problem. Maybe R1, the convergence fast is very fast. R1 directly is forwarding to R4, but during this time, R4 is still not to finish the convergence. R4 thinking going to the network 1, it should go here. Because based on cost, here is 100 and here is 30. So R4 should go back to R1. But R1 thinking I should send into R4. R4 thinking should send into R1. So here's the problem. Here's the problem for FRR. I mean, without any algorithm. There will be a micro loop. This is what we call micro loop, okay? So what to do? There will be some algorithm, some calculation way to do the forwarding to prevent during FR this kind of thing happen. So there will be, first it will be RFA, remote loop-free alternative. Loop-free alternative. This is what it is alternate. What does RFA mean? RFA. So normally the RFA, the traditional version of RFA means from R4 going to the destination from here to here. The cost should be lower than here to here. Otherwise, I will not setting this as a backup path. Okay, means R4 going to the R3, the cost should be lower than R4 going to R3, which means this cost maximum is 29. If it is 30, it will be a problem. 31, it will be a problem because R4 may got a chance to go this way. So this is LFA, but you can see there's a lot of network. For example, my cost is 100 here in this path. So LFA FR cannot be used. So there will be another type of LFA called RLFA, remote LFA FR. Remote LFA FR. What is remote LFA FR? Let me take another example. So the remote LFA FR means this. That this is to this point. This is network 1 from R1, R2, R3, R4. The usage scenario for the ILFA is a little bit. That will be how do I say this? It will be a little bit wider than LFA. I mean, more usage will be used if we use more usage scenario will be have if we use ILFA to do the calculation. Okay, so ILFA is thinking like this. I must find a point. I must find a node that going to here is smaller than going to here. Cost it will be going back to here. I find the fast point that, for example, R1 is want to do the FR. So R1 will finding the fast point that this cost is smaller than this cost. They find the faster. The most away from R1. They find those devices. For example, how do I say this? Let me give you an example. Let me thinking. This is 10. 15, 40. No, not 40. Let me do the calculation. 30 should be 30. Okay. So the R1 will doing like this. They will find R2. They will find. Let me do the calculation whether this is right. 34 to 35, and here come back. Here come back is how to do the calculation? I forgot a little bit calculation way, but anyway, R1 and R2 for RLFA, they were finding something called a P zone. P zone. P zone means those nodes when the packet is sending to this node, I can guarantee there will be no macro loop. So those nodes together we call it the P zone. And R4 will also do the calculation from R4 to those points if there's no loop. For example, this also R2 and R3. For example, R3 can fulfill this need. For example, R4 to R3 there will be no macro loop. We call it a Q zone. And the P zone and Q zone, if there some node is overlapped, we call this node is a PQ point. So I just sending the next hop to this PQ point. It will be okay. It will be okay. We can use a tunnel sending to the PQ point. Then PQ point can help me to forward to its destination. Okay. So using this PQ zone, the way to do the scenario to do the FR is extended. There's a more scenario can use FR, but IRFA still have limitation. What if the P zone and the Q zone is not overlapped? So there will be no PQ point. Then I cannot calculate the path for IRFA FR. So the TIRFA FR will doing something different. For example, in here we have the P zone. Let me see. Yeah, the P zone is here. The Q zone is here, which means P, Q zone do not overlap with each other. So during this time, from R4 to R2 to R4, we can use the SR, force the traffic forwarding from R2 to R4. This is TIRFA, topology independent RFA. What is this do? Because from south point to the P zone, any point in P zone, there will be no micro loop. From destination to the Q point, any Q zone point, there will be no loop. So which means I can just use the segment routing, force the traffic forwarding from this P point to the Q point. Then this Q point can send forward continue. So there will be no macro loop, will be no macro loop. So this is TIFA. It can, no matter which topology, what is the course it is set, there will be no limitation. I can always calculate a loop-free backup path. So it's like that. Just some example here. Whether you use path protection or node protection, it is all okay. A configuration will be very simple. By the way, TIRFA FR do not need controller. Do not need a controller. This is TIRFA you can use in any scenario. Without controller, this always can be used. Because ISS knows the topology. They have the capability to forwarding from one point to another point. So this can be used like without the controller, no problem. Okay, another one is anycast FR. Anycast FR. So what is anycast FR used for? For example, I was creating some how do I say this? I was creating some segment list. The path is from 1004, 106. It should be sending to this first and send to this. But this point is filled. R4 is filled. When the R1 trying to send into 1004, there's no 1004. How can I sending forwarding, continue forwarding? This is a limitation for TIFA FR, which means if the endpoint node is filled, the TIFA FR cannot work anymore, because TIFA FR means if I want going to the destination, I will finding any way. I will finding some way to get to this destination. But now this destination is gone. Where should I send it to? This is a limitation for TIFA. There's no place to go. even there's a many places. I can go from here, I can go from here, but R4 is filled. How can I do the TI-RFA? So under this circumstance, we can use something called anycast. Anycast, basically, they are putting two devices with the same node seed. They put R4 and R5 with same node seed 16100. And if R4 is filled, no problem. I will send into another 16,100. I was sending to here. Then here will help me to send into the destination. So this is anycast FRR. This is in case in some node that this path must like by last forwarding by this node. So if this node got problem, you can use anycast FR to prevent this kind of situation happen. Okay, so no matter TI-RFA and anycast, no matter TI-RFA FR or anycast FR, they are just what I said. This is just for temporary result. This is just for temporary result. Okay, so if any of those happened later they will change into another path. I need to say this again. TI-RFA, FRR, those kind of FRR, they bypass this is just a temporary way. Because when they bypass it, they actually need to add extra labor inside it to guide the traffic from here to here. So this is not a long way to do it. So eventually they will choose a backup path, end-to-end backup path from here to here and going to the destination. Okay, so this is hot standby. Hot standby, you can do the configuration statically or maybe use the controller. Okay, and hot standby also got limitation. Because hot standby, they have some, for the path, the source and the destination should be still stay same. I mean, from one point to another point, and with the color, it will define one tunnel. The backup tunnel and primary tunnel, backup path and primary path, they have the same source and destination. So what if the destination is filled? So this primary path and backup path, there's no this path anymore because my destination is filled. I cannot send into here anymore. Okay, we know, right? The tunnel have a source and destination. If the destination filled, even your backup path, you cannot get anything. So how to do it? What to do it? To save this, we will use another technique called VPN-FR. VPN-FR means when the BGP, no matter you use eVPN, VPN v4, VPN v6, when they sending the root entrant, P3 will send one, P2 will send one, and P1 will both get it. But we know by default, the BGP only selects the best route. So with the VPN-FR, the P will store, they will use P3 from P1 you go to P3. This as a backup path. So if the P2 is filled, which the routes will be withdrawn. The P1 will withdraw this route because it detects the other end is filled. I will withdraw this route, and the P1 will directly use the backup routes, which is going to P3. Then all the traffic will switch to P3, and it will use the kernel from P1 to P3, use another kernel. You can say this is kernel 1, this is kernel 2. Although kernel 1 have one pass and a backup pass, but since the destination is filled, I need to use another kernel and use another policy. Okay, so this is VPN FR. Any question? Okay, then let's move on. Here's some example. Here will have some how is protection is switching. First, like if some node is filled, I can use TIFA FR to do the protection to get to the destination. And after that, after a certain time, I discover that this path got a problem. I will switch over to hot standby, switch over to the backup path. And if the policy is filled, the policy, I mean the end, the destination end is filled, then we will use VPN FR to select the best path. We'll choose another kernel to forward into its destination. Okay, so this is VPN FR. Any question for those three type of protection? TIFA, hot standby, VPN FR. Okay, no question. Let's continue. Okay, beside those kind of FRR, this is all in case there's something happened. This is like if link broke down, the node broke down, how to do it. And there will be some other protection technique, macro loop avoidance. So about what is a macro loop, I already mentioned before that this picture. This one. When we talk about the FR, we already mentioned what is a macro loop. Okay. So this macro loop, I mean for the FR's macro loop, this is already can be solved because we can when we're doing the FR, we will use the LFA, ILFA, TILFA to prevent that. But macro loop is not just happened in the FR. Some other situation will also happen macro loop. Will also happen macro loop. So about the detail of the macro loop, it will be like this. Here I just gave a few examples that how is macro loop happened. When we talk about SRv6, we will give more example about the macro loop. So if you got any question for the macro loop, you can ask during SRv6. But here we gave a very simple example for the macro loop. This is for the traffic switchover scenario. That's from normal state to switch to the like backup state. Okay, it's like this. For example, in this part, the P1 want going to the P2. As let me check. Yeah, I want to go into the P2. So normally P1 will sending the packet to here. We're sending the packet to here. And unfortunately, that this path, sorry, let me check. Okay, it's like this. Sorry, wait a moment. Okay, so this micro loop happened in this way. First, the packet was sending to the P1, sending to the P1 because I want to go into the P2, and then the the P1 before there's something happened in R2, in P2, sorry, in P2 is something happened. Then the P1 will sending to the P3, and P3 will continue to send. But later, when the P2 is recovered, so the P1 they will not to do the FRR. They will not send into P3 because it knows that I do not need to use the P3 to send into a P1. So the P1 will send into the P2. But during this time, P1 is already being converged. But the P2 is just a start. It's just recovered from better situation. And the P2, during that time, they are not fully converged. This thing can go into P2, they might need to go into here. They might need to go into here. So the P2 will send into P1, and the P1 will send into P2 again. So during this time, we can use this avoid micro loop, those things to prevent some micro loop avoidance. Okay, but this is just one example, one scenario for the micro loop. There's many. Tomorrow, when we talk about SRv6, we will talk about more scenario like where you're gonna run into this micro loop situation. Okay, so here the example. And for the TIFA and the macro loop, there will be they are different. Okay, because some students when they learn about something about the RFA, they were thinking the RFA can prevent the FR, but can prevent the macro loop, but actually it is not. The TRFA, the purpose is different. For the TRFA, purpose is to locally compute a backup path for destination address. That's all. As long as they calculate based on some formula, calculate the backup path, it'll be all. But for the macro loop avoidance, it is just trying to prevent a temporary loop during the update of a primary path. This situation have this macro loop avoidance. This macro loop will not just happen for the FRR. For some other situation will also happen. For example, some devices the convergence time is different. This will happen macro loop, not just for FR. So the TRFA FR, they are just have some a very small scenario for the macro loop. Just the FR scenario for the macro loop, I can use TRFA to prevent. But a macro loop, this situation not just happened in the FRR. Some other scenario also will happen in FR. So their purpose is different. Their purpose is different. Okay, so then let's move to the BFD and SBFD. Okay, so and in the SR, we must find some way to detect the link, whether this is a problem. So we will have two ways. We can use BFD or we can use SBFD. But BFD for the segment routing, it will got a little bit problem. We got a problem for the BFD because for each end, if we use BFD to do the ping, it may not. In some scenario, it will got problem. The BFD will not be able to get up. So we'll use SBFD. SBFD. So so you can say for the BFD, if the BFD detects a large number of links, the negotiation time of the state machine is prolonged, which is not suitable for SR, for segment routing. So there's the SBFD. SBFD doing what? SBFD working like this way. You can say there will be in initer. It will sending a BFD, sending to the reactor, which will be the other end of the segment SR kernel, and the reactor will send back. It will a little bit like one arm mode for the BFD. This is similar for SBFD. This is you can think SBFD is like one arm BFD, similar. They are similar. So sending out and send back. If I receive the reply packet, I was thinking, okay, this kernel is okay. Okay, here is some like how is SBFD implement. At the very beginning, they will discuss the port or the time they're going to use. So we will exchange the SBFD control packet. Then the SBFD will ping. SBFD will ping. Okay. And like as we said, the SBFD is similar with one arm BFD. Actually, it's similar. So if you want to use a one arm BFD in SR, this is also okay. Like if you want. Okay, so this is segment routing kernel protection and detection technology. Any question for that? Okay, so if there's no question, let's look at the next topic. Typical usage scenario for segment routing. Okay, so first, we can use SIMPS-BE to do the forwarding. And also we can use, this is inter-AS, SIMPS-T also okay. About those two, I guess we already have ideas, so we just pass. Policy, same thing. And besides that, in the inter-AS, we also have sometimes between the AS, we also sometimes need to establish the forwarding path. So this is where the inter-AS E2E technology will use. This E2E technology actually is not difficult. Basically, we just use the BGP egress peer ingress, this EPE technology, to exchange, to forward the label. That's all. That's all. No, nothing different, nothing difficult. There's SR, for example, ASB1 and ASB2. ASB1 will tell the ASB2 like what is like what is the label information, like my export label is what. ASBR1 and ASBR2, they will assign the seed for the EPE peer. For example, ASBR1 and ASBR2, they are establishing a neighbor relationship, and the ASBR1 will assign the ASBR2 this neighbor relationship. They will assign this neighbor relationship as a 304, and ASBR2 will also assign, if the traffic wants send to ASBR1, the number is 403. 403. It's like this. So, for example, there's a traffic came in, and if it wants sending to this AS200, they should add a seed 304. So the ASBR won't receive a seed 304, it won't know that I should send it to the ASBR2. So this is EPE. So basically, EPE means I will assign the seed based on the BGP peer. For this BGP peer, I will send in 304. Another BGP peer, EPE peer, I will send in, for example, 305. Okay, so they are based on the BGP peer to assign the seed. So this is what is BGP EPE used for. Okay. So let me see. Okay, so this is scenario. And the rest will be the configuration, like how to do the configuration for SRB, how to do the configuration T, and the policy. Let's give a quick look, because tomorrow we'll do the demonstration. So here we just give a quick look, it will be enough. So this is level 3 VPN for the over SR MPSB, how to do the configuration. Very simple, that we set the sRGB, we set the index, and then we configure the VPN in PE. So we can say this is just a normal configuration for the BGP VPN v4. And then we'll try to select the tunnel. Then it will be okay. Then you're gonna see here we have a label. This label is being assigned by the device itself. It is a private label. Okay, it's a private label. This 48122 stands for the VPN, stands for the CE, where the CE belongs, that VPN. Okay, the concept is the same with will be same with what do you call it? Same with the MPS BGP VPN, the private label, the same concept. And for the level 3 VPN over SIMPS BE, they can have only one label, will be okay. One private label, it will be okay. And about TE, similar. We set the sRGB, then enable the T for OSPF, and ask the OSPF to use RSS also. EC is also okay. You ask EC to forward, or OSPF to forward to a device my node ID, node seed. You can see it is index 1. Then for PE, we can set the explicit path. Right? 2, 3, which means I going to P first, then going to PE2. Then we establish a tunnel, create a tunnel, setting a tunnel ID, signalizing. The important thing is here, setting the path, explicit path T1. Okay, then we send. And the BGP also we can do the configuration for VPN, do the peer for VPN v4, and doing the tunnel select, tunnel policy, and it will be okay. We can do that. It will be those forwarding. Okay, and the last will be for the SR policy. So SR policy, the basic configuration will be similar, like segment routing. Then here we can set some seed. This seed is static configured, but if you want to, this seed is for what you call the node seed. But if you want to configure, sorry, this is for adjacency seed. Sorry, this adjacency seed you can configure or you can leave it here alone. It's all okay. Okay, here just example that you can configure static seed, static adjacency seed, but you do not want to configure, also okay. And the rest part is similar with the SI-MPRS TE. Here's the P and the P2 to the configuration. Then a very important thing is here that you need to give a color, because we can say their color is 100. This is for the segment TE policy, SR policy. Color is 100. It means the color, if you want to, from P1 to P2, you can say P2, the loopback is 3.3. If you want to go into here, the color is 100. This define a tunnel. And you can define, okay, what is the segment list? What is a binding seed? The binding seed is a stitching seed, that one, binding seed. But here we do not have any binding seed, so you can configure it or not. Okay. There's another static adjacency. Oh, sorry. Then you can configure some root policy, and for some root, for example, for this root entrant, you can apply a color 100. It means if I want go into this IP segment, I will go into this path. So you can say we have a color here. This is a path. This is a segment list path is here. This is the path. Okay. It means if I want to go into here, I will go in that color kernel. Then later you can check the information. And it will forward out. Okay. So basically this is for the SR-MPRS. Okay, any question for the SR-MPRS? Okay, so if there's no question for the SR-MPRS, I guess this will be the training for today, and we'll see you guys tomorrow. Tomorrow we'll talk about the SRv6, and we will do a little bit lab demonstration for SR and SRv6. Okay, so see you guys tomorrow.